Electron configurations. So quantum mechanical theory describes the behavior of electrons. Electrons exist within orbitals, and when we describe which orbitals contain electrons, that's called an electron configuration. So as an example, this is the electron configuration for a hydrogen atom. It has one electron. That electron is in the first principal energy level, in the first orbital, the lowest energy one, which is S, and this is the number of electrons in the orbital. So 1s identifies the sublevel, and this tells us how many electrons are in there. You should have seen something like this in your previous chemistry class. So you can calculate things for hydrogen using Schrodinger's equation, and that shows us that they always occupy the lowest energy orbital. And this makes sense because everywhere in nature things tend towards lower energy, right? A ball rolls down the hill because that lowers its potential energy. Balls do not spontaneously roll up hills, do they? Water does not flow up the mountain. It just doesn't happen. So when we look at multi-electron atoms, now things get so complicated that you can't actually solve Schrodinger's equation, but we can have approximate solutions. And they show that the orbitals of these multi-electron atoms are like hydrogen's orbitals. We have two additional concepts that can make things a little more complicated: electron spin and energy splitting. So orbital diagrams are another way to represent where the electrons are. And as the name suggests, diagram, it's more visual. So the orbital diagram is going to have a box for each orbital, and it's going to indicate the electrons as half arrows. And those arrows can either be pointing up or they could be pointing down. Now that would be helium. So that up and down part is that last quantum number, the spin. So we talked about that as being like a Beyblade top that spins clockwise or counterclockwise. By convention, up is positive, down is negative, and we always put them in up first and then down, just because. But in a group of hydrogen atoms, roughly half of them are spin up and half are spin down. So it doesn't really matter. The Pauli exclusion principle tells us that no two electrons in an atom can have the same 4 quantum numbers. This is like saying no two individuals in the United States can have the same social security number, right? Everybody gets their own unique number because that specifies you as a person in this country. A set of 4 quantum numbers specifies 1 electron in an atom. So if we have electrons that are in the same orbital, they're going to have 3 identical quantum numbers. The principal quantum number, the magnetic, I always forget the names of these. Anyway, N, L, and M sub L, right? So each orbital can only have 2 electrons because to get a different number, we've got the plus 1/2 or the minus 1/2. Knowing, we can predict the maximum number of electrons. This is not worth talking about. So this would be helium. Here's its electron configuration. There's 2 electrons in the 1s. Here's its orbital diagram with 1 electron having spin up and 1 having spin down. These are the quantum numbers for those 2 electrons. They are both in the first energy level. That's where the 1 comes from. They are both L equals 0. That's the S, right? They are both M sub L equals 0. That's the specific orbital. There's only one kind of S orbital, right? And so far they have the same numbers. They can't have all 4 the same. So 1 is plus 1/2 for the spin, and 1 is minus 1/2 for the spin. And we indicate that by 1 arrow up and 1 arrow down. So for hydrogen, the sublevels S, P, D, F in a principal energy level all have the same energy, and that would be, we'd say they are degenerate. They have the same energy. That's not true in multi-electron atoms. The sublevels have different energies. They're split. And this is caused by charge interaction, by shielding, and by penetration. In general, though, the lower value of L in a given principal level, the lower energy of an orbital. So if we were talking about, say, n equals 5, and these are the orbitals, the sublevels, S is lower in energy than P, and D is higher in energy, and then F is the highest in energy. We need to understand the basics of Coulomb's law. And that's the whole thing, but we can also say it's proportional to the charge of one thing times the charge of the other thing divided by the distance between them. So if Q1 and Q2 are both positive or both negative, then E is positive, and that's like high potential energy, it's unstable. If one of these is negative and one is positive, then the energy is negative, and that's more stable. It's lower, like below sea level, kind of lower. So when these are larger, the energy is larger, and when R is larger, that makes the energy smaller, right? So the strength of the interaction between opposite charges gets stronger as they get closer together. And magnets behave that way also, right? So we have multiple effects here. We have the nucleus attracting the electrons, because opposite charges. And then we also have electrons being repelled by other electrons, right? And some of that is from electrons being between one electron and the nucleus, effectively shielding it, so that its charge appears smaller. So we call this the effective nuclear charge. It's the amount of attraction that an electron feels for the nucleus. I think we're getting to a picture. The closer you get to the nucleus, the more attraction it experiences. The better an outer electron is at getting into, penetrating the cloud of the inner electrons, the more attraction it'll have. And the degree of penetration is related to the radial distribution function. We'll explain that in a minute. Okay, pictures. Love pictures. So this is a lithium atom. It's got 3 protons in its nucleus, so a positive 3 charge. And here are 2 electrons in the first energy level, 1s, and this one is in the second energy level, which is bigger, right? So on average, it's farther away from the nucleus. So as this one views the nucleus, it also has these 2 negative charges. Remember, they're not just individual particles, they're standing waves. They're kind of all over the place. And so that shields this electron from seeing the full charge. Okay? So here's a stupid analogy. You go to the beach, and there's this person with this great body, right? And they're just like beautiful, and you're very attracted to them, right? And they're wearing almost nothing. You can just see them in all their glory, right? That's maximum attraction, okay? What if they put on a parka and snow pants and a face mask? If you didn't know what was underneath, would you be as attracted to them? No, because you're being shielded from their glory, right? The clothing is getting in the way, right? So these inner electrons are like putting a parka on the nucleus. And so this now just, sees a little bit of eyes and nose sticking out or something. But if the orbital that this electron is in allows it to penetrate to get in, then it can like unzip the jacket and peek in and see, oh, right? You see what's under there. Does that make sense? So if we look at those radial probabilities, this is the 1s orbital. It's literally off the chart here. And now we're going to look at the 2p orbital and the 2s orbital. The 2s orbital has this node here, but this part of the 2s orbital is inside of the 1s orbital, right? This is like inside the parka. So it can see the full glory of the nucleus, perhaps. So this, because we have this piece that's inside, and also this little section, the 2s electrons are more attracted to the nucleus than the 2p electrons are, because they can't get as close, okay? So the 2s orbital is lower in energy than the 2p orbital because the shielding is not as perfect. So because of all of that, the sublevels are not degenerate. We have the S sublevel, and then the P sublevel is a little higher in energy, and then D, and then F. When we get up to the fourth and fifth principal levels, things get so jumbled together that now we find that the 4s orbital is lower in energy than the 3d orbital, which doesn't seem right, but that's how it is. And part of that is because as we get further from the nucleus, higher in energy, the difference in energy between the sublevels becomes smaller and smaller and smaller. And so the difference in energy between 3D and 4S may not be very large at all. And so that's why the 4S can fill before the 3D. So this is general ordering of orbitals. We've got 1s, and then 2s, and then 2p, 3s, 3p, unexpected, 4s, and then 3d, and then 4p, and 5s, and 4d, and that's just like, wow, right? And you may have seen, you can draw a diagram and draw zigzag lines through it to get that order. I'm going to show you that it's all on the periodic table. You don't need to draw anything. Okay, but this is where I see this as being like a hotel. And we're going to get to that slide in a minute, but, just, so this is the first floor, and this is the second floor, and that's the third floor, and this is the fourth floor and the fifth floor. Okay, so this is n equals 1, 2, 3, 4, 5. On the third floor, we have 3 different sublevels. This is one room, and this is another room, and this is another room, and each of those orbitals are beds. So we've got 3 rooms in the hotel on the third floor, and the first room has 1 bed, the second has 3 beds, the third one has 5 beds, just because. I can't figure that one out. I've never seen a hotel that had 5 beds in one room. Would have been handy when we were traveling with 6 children. So the electrons occupy these orbitals to minimize the energy of the atom, so they're always going to go into the lowest energy orbitals first. If we look at orbitals in the same sublevel, they have the same energy. So let's go back here. What we're talking about there is these are 3 orbitals in the 2p sublevel. They have the same energy. Up here, this 4D sublevel has 5 orbitals. They're all the same energy. So in the hotel analogy, each of these beds costs the same amount to sleep in because they're all in the same room, right? Oh, you're going to go to the 4D room? This is the cost for that room. They're not going to come in and see who's sleeping in which bed. That would be weird. Orbitals can hold no more than 2 electrons. And this is because of the Pauli exclusion principle. We have to have 4 quantum numbers and a unique set for each electron. So if you're in the same orbital, you've got the first 3 the same, so the 4th one has to be different. The spin has to be opposite. And then Hund's rule says that when you're filling degenerate orbitals, electrons fill them singly first with parallel spins, and I'll get to that. Okay, The Quantum Hotel, my favorite analogy. A discount resorts for electrons in Mrs. K's chemistry land. So chemistry land is this imagination, and there's all these things, and gas atoms and things happen up there. It's a happy place for me. So in this hotel, it's a multi-level hotel. The first floor has one room, and that's called the S room. So a lot of buildings are numbered, like, things on the first floor rooms are 101, 102, 103. So here it's 1 and then S. On the second floor, there's 2 rooms. There's 2S, and then there's a 2P that's further down the hall. The third floor has 3 rooms, S, P, and D. The fourth floor has 4 rooms, S, P, D, and F. The hotel can label these rooms whatever they want. The S room has 1 bed. The P rooms all have 3 beds. The D rooms have 5 beds. The F rooms have 7. That's at 1357, and that has to do with how those quantum numbers are. Only 2 people per bed, and they must have opposite spins. What does that mean? So, well, I kind of worked on that one, because it's like, how to make this work without being too weird. Okay, so I once went to Fort Snelling, which is a very old fort in Minnesota, and soldiers lived there and defended the West from the indigenous peoples. Not necessarily a good situation there. But anyway, these guys needed to stay warm in the winter, and it can be 40 degrees below zero. That's a wind chill. That's just absolute temperature. And this was like in the 1800s, right? So they didn't have heaters and stuff. You got all these soldiers trying to keep warm. So these wooden barracks, and they had these bunk beds. And I actually saw them. It was really kind of cool. So the bunk bed, this is just the bottom one, it's narrower than a regular twin bed, and 2 soldiers slept there. What? They did that to keep each other warm. Okay, not because they liked each other, but to keep each other warm. And they were like very, very fully clothed because it was really cold. So the way they fit is one guy would sleep with his head at this end, and the other guy would sleep with his head at the other end. And they could get close together that way and keep each other warm. So this is what I mean by opposite spins. Okay? This guy sleeps with his head at the head of the bed, and this guy sleeps upside down. Kind of goes along with the arrows too. Here are correlations. The floors of the hotel represent principal shells or levels. Each room is a subshell. Each bed is an orbital. Each person is an electron. And money is the energy. So this is like the elevator, right? And again, we've got floors. And the floors are not slanted. Oops, I did that one wrong. The floors are not slanted. This is representing, the height here is largely representing the cost of the room. So this is the cheapest room, and this one, and then this room with the 3 beds, and then this one, and this one, and then this 4S room is cheaper than the 3D room. Well, why might that be? And why is S cheaper than P? Well, this is the elevator. It's kind of loud by the elevator, and the ice machine's there, and so if you want peace and quiet, you don't want to be right next to the elevator. So this room is right next to the elevator. That's always the cheapest on each floor. And here, this one's far enough from the elevator that it's so peaceful and tranquil that this one's cheaper, even though it's on a higher floor. Okay? So when we're talking about electron configurations, unless it says otherwise, and it almost never does, we're talking about the electrons in the ground state in the lowest energy orbitals. We know how many electrons there are in a neutral atom because it's the same as the atomic number, right? Fluorine has 9 protons because it's element number 9. It has 9 electrons. Yeah. So the electron configuration is just a listing of the sublevels with how many electrons are in them. And this is, I think of as the guy at the front desk down in the lobby. He's got this list going, so when the next electron comes in, he can know which room to send them to. And he's like, well, this room's full, and, blah, blah, blah. Okay? Well, that can get long, especially for, that one's 36 electrons. That looks kind of long. What if you were doing lead, 82 electrons? You're just listing off a lot of stuff here, and the first part's always the same. So we have what's called a noble gas configuration or an inner electron configuration, and that is where we look at the previous noble gas. So if we're going to do rubidium, rubidium has 37 electrons, just one more than krypton. So here we have the electron configuration for krypton. So for rubidium, instead of writing all of that, instead of writing all of this, we can just write krypton in brackets. So this says the electron configuration of krypton plus 5s1. Okay? It only works with the noble gases. Okay, so we looked at hydrogen and helium. Here's lithium with 3 electrons. These are the orbital diagrams. So we don't draw them in that staggered up energy thing, except when we're learning about them, because it's awkward. So we're just going to draw them as horizontal boxes. But so here's the first floor. It has 1 S room. The second floor has an S room and a P room, but we haven't drawn that yet because we don't need to go there yet. Is it there? Yeah. If nobody is staying in a hotel room, does that mean it doesn't exist? And that's not like the tree falling, right? No, it exists. It's just empty, right? So there's all these orbitals just waiting for an electron to come and occupy them. But we're just going to look at the ones that actually have electrons in them. So here we have, this is how I think of it. So we've got 3 electrons. We're going to send these electrons into the quantum hotel and give them the cheapest rooms, okay, because they're very stingy. It's a discount resort. So the first one goes into the cheapest room and, of course, sleeps right side up in the bed, because who wouldn't? You can't sleep on the floor because the floor is lava. Okay. I know if four guys had to stay in a hotel room with 2 double beds, they'd arm wrestle or something to find out who slept on the floor, right? Yeah? You can't do that because the floor is lava, okay? So you can't do that. So the second guy comes in here, and he's like, somebody's already here. I'll sleep upside down, just less icky that way, I guess. Flesh that one out however you want to. And then the third one is like, comes in, and he's got to spend more money, higher energy, but he gets to go into the next room, and he happens to have his own bed. So beryllium has 4 electrons, and so the 4th electron coming in is going to have to share a bed there. Boron has 5 electrons. Any questions?